Okay. As a quick recap, keep in mind that there are 3 different t-tests that we did. The t-distribution basically means to resemble the set distribution to the normal distribution. We're basically utilizing a different way of quantifying the standard deviation, and based on that, estimating the variability of a distribution of a sample distribution. We're basically dividing now and doing the calculation of the standard deviation, dividing these sum of squares divided by the n-1 by the degrees of freedom. So that's the new concept to the t-distribution, the degrees of freedom. So then you have one distinguishing factor is always the number of samples you're actually comparing. And we know that if we have a normal distribution and we know what the standard deviation is, and we don't have to estimate it from the sample, we can utilize a set test, a set statistic, where we're basically comparing the distribution of means to the mean of the population. Then we have a single sample t-test where we're basically estimating the standard deviation that we need to do the comparison of the distribution of the means to the population mean. We again have one sample. We're estimating the standard deviation by estimating it from the standard deviation of our sample, using the degrees of freedom and this newly somewhat inflated standard deviation. Then we have the paired sample t-test and the independent sample t-test. There we're dealing with 2 different samples. Keep in mind, if it's paired, you will have some form of a chronological order. Basically, you have a before and after. So always read the questions carefully, make sure that you understand which cohorts you're dealing with and where the sample is coming from, whether it's the same sample and the same participants before and after, or whether it's 2 independent cohorts and 2 different samples. If it's 2 with different participants, we use an independent sample t-test where the distribution which we're actually comparing is the distribution of differences between means. Means, you're drawing from one sample population, a subsample and another subsample. You're calculating this difference, you're dropping the subsample back, you get differences for each time you do that, and you're drawing out these random samples. So you get a distribution of these differences between the means. Whereas with the paired sample t-test, your comparison distribution is mean difference scores. So the distribution of mean difference scores. So you have before and after, and you're calculating an individual difference score. And you use this mean to compare it to whatever your null hypothesis says. If your null hypothesis says there was no change from before to after, you use 0 as your null hypothesis. If you have an anticipated change, like various examples exist, one could be growth of a fetus, growth of a toddler. These are classic examples. If there's an anticipated change, you subtract that from your difference between the scores of the mean of these differences. So the approach is somewhat comparable between both. You have a difference, you're creating a difference, and you try to utilize a variability to characterize or standardize this difference. Based on that, you get a t-score. And the only thing that is, so you know how to quantify the t-scores based on the t-score table. Open this right away. So if you have a t-score table, you will find in the t-score table the information on the degrees of freedom, which is the sample size -1, gets you the respective degrees of freedom. And you will then determine the alpha level that you're willing to accept, which is the type 1 error probability that you're willing to accept. And if this is smaller than 5%, you will reject the null hypothesis and assume that there's a significant difference. And this is usually at 5%, 5% and two-tailed test, especially at the 3rd column here. And you find this critical value if in that standardization of your difference using that variability that you have determined, i.e. standard error of the mean, you will reject your null hypothesis and say that this probability of a type 1 error is smaller than the alpha. We've done that ad nauseatum, but I just can't repeat it over and over. It's just important to keep this in mind, and we're gonna do today some examples to see how this actually looks like in real life. So again, we have done examples like that repeatedly. It's just one more time doing that. So you have here 2 exams. These are 8 students on 2 different exams. So again, it's exam 1 and exam 2. It's different exams for the same students, which is clearly a paired sample t-test, right? 1017 in practice lab 3. Can you find that in practice lab? It's on module 18 on Canvas. You have practice lab 3 as an assignment. And this Excel sheet should be downloaded from the assignment. And we're gonna create today, there's also practice lab 3 solution R code, which is this. And this basically contains the same information. So you have an R code that is on there that basically gives you that code that will allow you to do the comparison we're doing now. And I will walk you through that, and it's super simple. So let's do it in Excel first, because that's what we're most comfortable with, right? So we're doing no, just do the R code, but just do it in the same fashion we did the practice labs, right? So the practice labs should be a low-hanging fruit where you make a couple of points. So that's kind of the idea. But really follow along, because it's kind of, so this is these printouts of the t-tests. This is what you will see if you do ever look at any statistics. You do your own statistics. That what you will see may not be from R, but it will have the same shape and form. Yes.
If we run the code at R, will we get the same results as if we did in Excel?
Yeah.
That's cool. So we can like check ourselves.
Exactly. That's kind of the idea, right? And that's why I'm doing this practice labs, because I want you to see that you achieve the same results with different softwares, and whatever you will be using, it always follows the same outline.
Are we gonna run the code after?
Yeah, let's run it at the end. Yes.
Where did you get this sheet?
Practice lab 3.
So I open up mine's different. And mine's also.
So you have to go to the bottom.
Yeah, it's the 3 different worksheets. Okay.
Oh.
All right, good. So yes, that was the first point of the practice lab. Okay, good. So you have 2 different exams from 8 different students. Paired sample t-test. What are we going to do first? We're gonna calculate the differences. So the difference here is exam 2 from exam 1 is minus 1 versus the other. No, we need to go fast. So it's exam 2 minus exam 1. So it's the calculation of the individual differences between those 2 scores. Good. So next we're going to do the following. Next we're going to calculate the standard deviation. For the sake of being fast, we're going to do STDEF as a function. Standard deviation STDEF. You know that function. You do the standard deviation of the differences, gives you a standard deviation between those differences. No, just a regular function, .s.
Wait, what's the equation? Do you do this one more time?
STDEF. You just calculate the difference and you do the standard deviation function.
Between which?
Exam 2 minus exam 1.
All of them?
Yep. So once you have a standard deviation, and that contains now this formula that we always did, sum of squares divided by the degrees of freedom gets you to the standard deviation. Once you have the standard deviation, you just need to calculate the standard error of the mean, which essentially is standard deviation divided by the sample size, which we know is 8. Standard deviation? Square root of that. What was your question? Sorry.
For standard deviation, it's STDEF, and then what do you do?
STDEF, the differences between exam 2 minus exam 1. SQRT 8. 8. It's 8
And
students.
the 8 students. Okay.
Yes. So you calculate the standard error of the mean.
Oh, I got the wrong.
Good old Excel, right? Okay. Okay, so you square root your calculation. So your sample size, square root of the sample size, and you divide the standard deviation F10 by your square root of the sample size. Gets you the standard error of the mean.
Do you have to send us this sheet afterwards? Do you have to send us this sheet?
Yeah, I'll post it up. That's fine.
No, an 8.
So since we have now a standard, we do have a sample size of 8 that gives us a degree of freedom of 7. So we know for an alpha of 5%, we have a critical T of 2.36. So this is our critical T, 2.36. At alpha 5%. So this is 2.36. So now we know it's super easy to calculate our 95% confidence interval. This is now lower limit, upper limit. So we do have a mean difference to calculate, which is mean equals average of these different scores. I know this goes a little fast now, but essentially we have done all of this to some extent, right? And you get the spreadsheet. Just follow along, right? It's like we're calculating a mean difference. We have a standard deviation. From the standard deviation, we get from the standard error to the standard error of the mean. We calculate, or we basically estimate a critical T, which is just our 5% alpha. And then we're getting to lower limit and upper limit. And that's simply done by calculating our mean difference minus the critical alpha multiplied by the standard error of the mean. So that's our critical. Multiplying standard error of the mean multiplied by the alpha, the critical T. It just looks a little faster than it is. So you have a mean difference plus 2.36 multiplied by the standard error.
I'm stuck on STEM. I'm stuck on step number 1. Can you just go over quickly?
Okay, so difference.
Accept the no hypothesis.
Oh, we're really fine. Don't even.
Okay. Okay. Everybody focus. Okay, so we're doing a difference. We're calculating an individual difference. We're calculating the mean of these differences. That's the average function.
So how do you do that?
Average of these 8 differences.
Average.
Yep.
And then
So-
when you press.
Yep. Then we get to
Equals average.
equals average and these 8 differences. Then we get to the standard deviation. From the standard deviation, we get to the standard error of the mean.
So what do you press? Equals standard deviation. Equals STDV. That exactly.
That is the formula.
And what do you do for STEM?
This one.
Equals F10.
F10 is the standard deviation, and the standard deviation divided by the square root of the sample size.
Divided by square root of
8. Okay, so this is our 95% confidence interval. So what do we know? It contains the 0.
yeah.
What does that mean?
It contains the critical value.
No, it contains the 0. It contains 0 change,
Except.
meaning we're accepting the null hypothesis. Correct. Correct. And we can do then essentially a calculation of the T, which is basically the difference divided by our standard error of the mean, which basically gets us to a T of 0.62, which we know is smaller.
What did you do? What was the last step of the T?
That is the division. So this is the difference. So you do, the formula essentially is difference minus 0.
It's the mean divided by.
It's the mean difference minus the null hypothesis divided by the standard error of the mean.
And you always assume that we're talking about 0.
Yes, because there's no anticipated change. If you would say, I want to know whether I know that all students will improve, and I think that improvement will be greater than 0.5 score, then 0 would be 0.5.
What does T stand for?
You could make it a one-tail test, yeah.
What does T stand for?
If it would be, that would be a one-tail test essentially. If you say I hypothesize it will be improving, then your null hypothesis no, they're not improving that much. Then this becomes 0.5 or 0 or 1 or whatever you anticipate to change, because you're subtracting from the mean difference, you're subtracting your null hypothesis. Yeah.
How'd you get negative 3.48 and 5.8?
That is the calculation of the standard of the 95% confidence. Not this. That is the calculation of the 95% confidence interval, which is basically done by C12, which is our mean, minus the standard error of the mean multiplied by the critical T.
How'd you get 2.36?
That is the critical T comes from the T-score table.
That's like critical.
That's this here. That's the alpha. That's the critical T. Yeah. So you have a sample size. Sample size minus 1 gives you the critical T, gives you the degrees of freedom. These corresponding, the corresponding value in the respective column that you're interested in, which indicates your alpha for a two-tailed test, gives you that critical T value, right? Good. So now let's look at this in R.
Do we need to have everything filled out for it to work? Because I'm still.
Well, no. R will work by itself. But I just want to show you how simple that is. So hypothetically, you can also do the following. Let's go back to Excel. So this critical T, you can hypothetically also do the same thing by doing equal sign T dot test, and we've done that formula. T dot test, array 1 is exam 1, array 2 are all the entries for exam 2. If we go on the formula builder, you remember this, we did that, right? So we have array 1, array 2, we have the tails, we know how many tails, right? We have 2 tails. So we hypothesizing a change in either direction. And we need to specify the type of test. So we have paired, 2 samples with equal variance or 2 samples with unequal variance. Now we have paired. We have a paired test.
What's the comma 2? Why is there a comma 2?
So comma 2 is, so we have array 1, that's this in the first. This is array 1. This is array 2, this is tails, and this is type. So comma indicates these different 4 entries. So we have array 1, array 2, tails equals 2, and type equals 1, 2, or 3 is either paired, 2 sample equal, or 2 samples unequal.
It doesn't work for me. It says
Okay, just open the formula builder.
it says I enter too few arguments for this function.
Well, then you need, okay, then open it up. Open D dot test. Open the formula builder by clicking here on the FX.
Yeah.
Then you get here to this menu. And here you enter array 1, array 2, tails equals 2, because it's 2-tail test, and then type equals 1. Yes.
What is type?
Oh, type is this down here. So you have 1 equals paired, 2 equals 2 sample equal variance. No, we're doing paired. It's a paired test. Yes, it's the following 2 different exams in 8 equal students. So it's one group, it's 1 sample over 2 exams. So we're doing a paired sample t-test. That's the chronological order, right? It's like I have 8 students and they write 2 exams. That's paired. Same group.
How do I go to the formula builder?
By clicking the FX on the left tab here. fx. Yeah.
Should we enter it?
Yep, you can enter.
Okay, on one, and then
If you click then on done,
click done.
yep. With done, you get here 0.55.
Wait.
And this is your p-value.
Oh, I got that.
And this is because it's larger than 5%, you know already it's non-significant. So accepting the null hypothesis was the right thing to do.
Which means it'll be.
Which means it's not.
Oh.
0.05, yeah, if it's smaller than 0.05, you're rejecting the null hypothesis. If it's greater than 0.05, if it's smaller, you're rejecting. No, if it's bigger, you're accepting the null
I got a
hypothesis.
different number. I got 553.
Because the t-score, has a correspond. Remember the set score. Yes. So they are the percentages, right? And these percentages of the normal distribution get smaller with a larger magnitude of the absolute value of that set score. Same with the t-score. If you look at the t-score, this is the probability of you rejecting something that you shouldn't be rejecting. So basically, the greater the t-score, the lower the p-value. Exactly. That's the probability of a type 1 error, that you're rejecting something that should not be rejected.
So the p value is less than the
Alpha, yes.
than alpha, which is 0.05,
Yep. Then it's significantly different.
and you reject it on it.
And you reject the null hypothesis.
And
Correct.
alpha in our case is 0.05, right?
0.05, correct. Correct.
Oh, apparently we got a different number. Can you read your number? We got the
0.55 or 56, right?
55, well,
55. Yeah.
30832. Oh, we got 308315. I just you like cut it off. Okay.
Yeah.
Okay, we're-
So if you open it up, it will give you more. Yeah. Okay. And now to R.
Yeah.
If you open the same practice solution, and there's the solution script. You have first line, you always clear. Here on line 6 and 7, you just enter control and enter, it clears it. So now it automatically jumped down to 4, which is the next line where something is written. Control and enter just makes it jump down. Now it's empty. So the environment here is empty. If you now again press control and enter, it will run to the next operative line, and it will jump over and execute line 6 and 7 and create here a data frame that you can look at. So if you look at this, you're opening here and separately. It should look the same. So these are the same. These are the same results and the same entries as on Excel. Correct. So now, if we were, yeah, you just go back on top. If you want to delete whatever was done before, for the submission, you just do again Control A and you run the whole thing down again.
What do you do when you?
Yes. So just two times. Oh no, one time gets you to line 4, a second time gets you down to line 8. And then you have here this object build. This is your data frame that you're working with. That's where I'm at right now. That's the current status. So if you go now down to line 12, so we want to know the t statistics, we want to know the 95% confidence interval, and we want to know the effect size. So simple, right? So line 12 contains the t.test function of Excel. And this is how you run it. Exactly. Control enter on line 12 gives you the paired t-test. So you have here a lot of information. You have here, yes, madam. What's up? No, do it on the first. Yeah, just go on the first line, press control and enter, and just jump down. It will do everything automatically. That's how I've set up the code. This is just, it's a sandbox for you guys. It's just playing around, right? And if well, it is. So if you look now at this result here, you have a lot of information in here. And this is usually from more sophisticated statistical software. That's pretty much the information you get. Okay, so what do we have? We have the two arrays, exam1, exam2. We see the t, which is 0.62. We knew that, right? We calculated by a degree of freedom of 7 with a p-value of 0.55, which is identical. The alternative hypothesis, the true difference is not equal to 0.
We can't accept that.
Do we think that's right? No, because our t is smaller, right? But this is, it developed its own alternative hypothesis. It states, it gives you the alternative hypothesis based on the data you fed. It gives you 95% confidence interval, which I hope is identical to what we have. And then you have sample estimates of a mean of differences. Okay. So far, so good. Yes. Line 12. Yep. Just press Control and Enter. It will automatically get you there. Sure. All right, good. Next. Now in R, you can do a little bit more sophisticated things. And that's where the fun starts. Because now you can, well, so this is A, right? So we have now the t-dot test, and you can take this result of your t-test, and R creates objects. So this, for example, is an object. But an object can be a data set, can be a test, can be a model, it can be whatsoever. Everything can be packed in an object. And this is what we're doing on line 14. If you press Control and Enter, you get now an object, which is basically t-test df1. So that's the t-test for our data frame 1. And if you click on that, you can either click on that, then you get this overview here. Here's the standard error, which is consistent with what we have. It gets you it gets you alternatives. It gives you all this information. If you go back, you can also query this. So if you do ls, you can always ask the object what's in you, what do you contain. So lsdf1 is the data frame. Gives you, hey, I contain exam1 and exam2. Exactly, just Control and Enter. If you do the same exercise with line 16, you get all these different entries. So this is what t-test df1 contains, and you can query this. You can explicitly get information out of your object by amending or adding the $sign and the respective sub-object to that object. So if you say t-test df1, which is our t-test, $sign p-value, it gives you just the p-value. So it queries, it digs into that object and just grabs that value it wants to have. And this is the value you want to be working with.
I should do Control Enter again.
Control and Enter gives you exactly that. Yeah. Yeah, just do Control Enter. You get exactly that out. If you go on line 19 and you say conf int, it gives you the content of the words.
Wait, what did you just do by 19? Yes.
t-test df1 conf int gives you and extracts you the confidence of the words. So you get each individual line item and sub-object in your t-test, you can extract it. And if you, for example, you would write in a report or whatsoever, you can automatize this to basically create you a table in Word or as a PDF. You can run this all as a PDF. And that's pretty cool. When you write a paper, this is super helpful. So now we want to lastly calculate the effect size. And that's a little bit more tricky because that needs to be done by hand. But if you calculate the effect size, you just need the mean difference of these two exams, and you divide it by the standard deviation, gives you the effect size, right? So we know that. So now the effect size is 0.22, and we have done that, right? Yeah. Just so effect size is now the difference divided by the standard deviation, and that is 0.22, which is consistent with that calculation. So if you calculate your t,
Difference or just the difference?
the mean difference
Divided by standard deviation.
by standard deviation, because you want to take the effect of the sample size out, right? That was the story.
Oh, it's the same.
Okay, so that was example number 1. It's fun, right? It makes life easy.
It's like a game. You have to know what you're doing.
Well,
I feel like I'm gaming.
it is with so statistic programming and this whole coding story. This is, if you master the main function, you can make your life tremendously easy. You can do so many
How do you
cool
learn
things
how
with
to
it.
code this stuff?
Well, you need to sit down and try things out. You need. So well, yeah, honestly,
Okay. Awesome.
it's you need to want it. And then you write me an email and I'll show you how to get that. But if you really want to learn R, there are plenty of platforms how you can learn that. A really good one is DataCamp. And it used to be previously for that course a requirement to do the first, but I've stepped away from it. I give you a taste of R, but I don't make you do the DataCamp exercises anymore. Because there was very mixed feedback on how useful it was. Let's put it that way. So it's really a decision essentially to either go deep into statistics or not. If you don't have need to do that and you don't want to do it, then you get through with basically just needing to interpret things. You can do a lot of analysis in Excel yourself. If you want to dig deeper, then there's always going to be opportunities for you to learn more. This course, I just mean to really give you like a little bit of a gusto piece where you can just look at it, digest it, go through it, play around in Excel. Those of you who will enjoy that, they will know where to find me or the pertinent information. So that's the idea of the practice lab. That's the idea why I add R to this course. So, but back to the main point. Okay, so that was example 1, super simple, super easy. Now we go to the second example. Same story. Pretty much the same application. We have score 1, score 2. Same thing. So now we know how to do it, right? So now we know difference.
How do we break from R? How do we run the whole code from R?
Well, we'll get to that. Command and A, you run the whole thing through. But let's do that in there. So we do score 1 minus score 2 minus score 1. What's different now is that it's a smaller sample size. As such, it will be different in the calculation. So we do a standard deviation, we calculate the standard deviation, but it follows the same layout. Right? Standard error of the mean is now standard deviation divided by SQRT of our sample size, which is now count of these entries. So standard error of the mean is 2.75, and we have now a critical T, which is different. So we have now 5 entries, 4 or 5 entries. So degrees of freedom is 4. So for 5%, we need to look at 2.78. So that's our critical T. That's 2.78 as well.
Yeah.
And that's simple, right? So now we have the 95% CI. Equals the mean minus this multiplied by the standard error of the mean. Same thing as before. So always keep in mind that if you have 2.78, do we think it's significant or not? Yep. What's your conclusion? What's the null hypothesis? What's the alternative hypothesis? And what's your interpretation? So what's the null hypothesis? That there's no difference. No difference. Research hypothesis, there's a difference. So what's your interpretation of seeing this mean and this 95% confidence interval?
It's within the negative 7.5. Negative 7.8 is within. Never these the limits.
It is within. That means, yeah, because it's arithmetically we calculated a lower limit and an upper limit. But these limits do not contain zero. So we're concluding that students got significantly worse from exam 1 to exam 2. So that's the conclusion. We're rejecting the null. And we conclude it was students got significantly worse from one exam to another.
Are you looking at the means of the comparison of the two means of the scores or not?
You don't need to. So also, well, that's actually a good point. Thank you for raising this, because if you calculate an average, and that's again an arithmetic principle, if you calculate two averages, and you have average 1 and average 2, the average of the differences of each individual entry need to be identical to the difference between the two averages. Okay, let that sink in. Okay, so the average of all the differences needs to be identical to the difference between the averages of both scores of both exams.
You add up the differences.
Yeah, so if you can also calculate this by calculating this minus this. It's the same result. That's important to keep in mind.
What
So,
we're saying, let's say the null hypothesis, there's no difference between the scores of test 1 from test 2 of test 1 from test 2.
that would be the null hypothesis. And the research hypothesis that there was a significant difference, or there was a difference. Correct. So, and these are our 95% confidence intervals. It does not contain the zero, meaning there was a significant change between those two, significant difference. Good. T easily calculated. We take the mean difference and divide it by the standard error of the mean. It's a T of minus 2.84, which is smaller. So it's more extreme than the critical T, which is 2.78. And since it's two-sided, it's either minus 2.78 or it's plus 2.78. At minus 2.84 is more extreme than minus 2.78, right? It's lower. I see some skeptical looks. Okay, let's go to, this was dependent sample t-test. Remember the example of, what was it? So we're looking at, we have 2.78 standard error as alpha. These are our critical T's. Critical T's are always two-sided. So this is plus 2.78. This is minus 2.78. Minus 2.84 is less than our extreme to the lower end. So calculating a 95% confidence interval essentially gives us here the boundaries. Right? Make sense? So we have basically, if this difference would contain zero, and this is around that mean. So if you would hypothetically, we would build it around zero, we have now SEM. We can look at it in a different way. If we do this around zero, it's standard error of the mean multiplied by 2.78. That's our upper end. And minus this, minus 2.8 multiplied by 2.78 in numerical terms would be, that would be the boundaries around zero. So our difference, that's 95%. That's 95% around zero. That is our null hypothesis. And if we look at this, this is exceeding this lower bound. We're just inverting it. We're calculating the 95% confidence interval around the difference is built around the mean difference. And we're comparing this to 0. So if we would build this around 0, this would be our null hypothesis. So if our difference would be between these two boundaries, which is nothing else but minus and plus standard error of mean multiplied by our critical t, if the null hypothesis were true, our difference would need to lie in between those two values. If we're inverting this and we're calculating the 95% confidence interval around our difference, meaning this is what we think the population confidence interval or the population mean will be in that interval, we are rejecting the null hypothesis because it does not contain 0. So there was a change based on our sample. And we believe that this would be the same in a population. Make sense? Kind of. All right. But this is basically how you get to a t of minus, yes.
I'm a little confused with the -7, like -7, like what you're talking about, where it falls in between.
So it depends on how you look at this. So the standard error of the mean multiplied by your critical t. The critical t is determined by your degrees of freedom. The standard error of the mean is based on this variability that you utilize to estimate the standard deviation of your population. So now you have this quote-unquote margin of error, right? That's the confidence interval. If you build it around 0 and you say, okay, so this is my null hypothesis, I don't think that there was a change. These are the critical values, and this is that value. If the null hypothesis is true, my population mean and mean of my sample needs to be in that interval, which we know it's not because it's 7.8. So now we take this margin of error and we're building this around our mean difference of 7.8. And thereby, it's minus 7.8.
So isn't that in between the interval of -15 and -21?
Yes, because that's how you calculate.
Yeah.
You
so
take
it
the
has
mean
to
difference.
be-
So it has to be.
It has to be in.
Exactly. But it doesn't contain the 0. If you build a 95% confidence interval around 0, it would need logically to, if the null hypothesis were true, logically contain your negative difference between score 1 and score 2, but it doesn't. So I just meant to illustrate this. Yeah. So now, as soon as you have a critical t exceeding your t exceeding the critical t, you know your difference is significant. And based on that, then the last thing we need to do is just to calculate an effect size. And that's always the same principle. You take the difference divided by the standard deviation. Gets you effect size of minus 1.27, which we know is a large effect size, right? 0.2 to 0.5, 0.5 to 0.8, greater than 0.8. Good. Always the absolute value. Keep in mind, don't get sidetracked. If you see a negative effect size, think about the absolute value. So drop the sign, only for the effect size. Good. All right, so now we go back to R. So that's our example 1020. So we're building now a DF2. This is line 24 and 25. We're pressing Control and Enter. We get DF2 built out. So that's our 5 scores. That's the same example that we have in the Excel spreadsheet. We're calculating now a PRT test. Oops, yeah, we didn't do it. Didn't do that. Okay, t-dot test. We do score 1, score 2. Oops. Score 1. Make sure to only capture the first 5. That would take array 2 is 16 to 6, 2 tails, and again 1 because it's paired. Gets us a p-value of 0.047. Simple, right? That is our type 1 error risk.
It's less than 0.05.
Correct. That's why we
You don't
reject it.
reject, but you-
We are rejected. Doesn't contain 0. Remember? The first one we do reject. That one we reject. Because the t is greater than 2.78, which is our prediction t. Right? So now if we do this in R, we do t-test df2.
On 30.
Hmm?
30.
On line 30, yes. We get the same list of possible sub-objects, and we get a p-value of 0.047, just like in Excel.
Oh wait, do you do control enter for 30 and 32?
You can do control enter down to 34.
Oh,
You can
all
also
of
do
them?
it all the way down. You can also do it all the way down to
Oh no, I don't know.
0.17 and 50.
If you're getting errors.
Errors.
That's not fun.
That's not. df2, yeah, you need to run line 24 and 25 first. So the t-test, the confidence interval is basically the same. The only thing that's different, and that's a little bit of a caveat, this is why you always need to visually also look at the data, because these here are positive.
They're what?
They're positive. So you need to know, and you need to always do descriptive statistics to understand essentially what you are analyzing. So if you only look at t-test, and this can always be done, I'm inserting here a line, which is summary, t-test, t-test underline df2.
Yeah, that's also.
Yeah. Oh. No, not summary, sorry. Not summary, just write t-test df2. That gives you again this overview that we had before.
You wrote that.
You
Wait,
see
where
it?
are you at this?
On 36.
Just anyway, just 36.
And
You
what's
do it
that?
as 36. Don't try to shift things down.
It didn't do anything though.
Fill out 36 and just run t-test df2.
And we dot control enter that?
Control enter. That gives you this overview. So what you have again, the mean of differences, and here the mean of difference is positive. So it basically calculated score 1 minus score 2. That's why it's positive. So that's always the tricky thing. That's why you need to pay attention what is subtracted from what. So you need to always numerically look at what the differences are.
Oh, so it just gives it to your positive.
It makes a difference if you subtract score 1 from score 2 or score 2 from score 1, it's either positive or negative. But it's a two-tailed test.
It
The
only gives you
result,
positive here.
yeah. But you can do this the other way around. You can basically you just have to multiply it by minus 1, and you're looking at the same result. So it's not making a difference in that regard. Okay, so confidence interval is identical to ours. If we would do it the other way around, we would get also positive values. We chose to subtract score 2 minus score 1. That's why we're getting negative values. But again, it's a two-tailed test. Same principle applies. Doesn't matter whether it's negative or positive. Yes, Matthew. Yeah. Just where did you mess up? That's a little imprecise, but okay. No, just go backwards. You just start with line 24. Just go back to 24 and run all the lines down to 36. You're fine. You can run this from every time.
How do you do that?
You just go back and just select whatever you want to run again.
And then click what?
Control enter.
Control.
Yeah. Yes. There's nothing to change. Just run the same thing down. Yeah. Yes. Yes.
How did you get to, what was the last thing you did? No, I don't have the 11.29.
Okay, 11.29. Oh, that's just, I inadvertently selected this. This is just a number of the example. So this is the example 1129. That's it.
I actually did the 37 also, so how do I take that?
No, just leave it. Yeah, just leave it. Just ignore it. Just ignore it. So everything that has a hashtag in front is just a comment. So you're just commenting. So I commented here, okay, so this is example 1129. And this basically is consistent with the number here of the worksheet.
I'm saying if I control
Enter.
entered it, it's fine.
Yeah. So again, comments do not take any action. So they don't really are being executed. They're just displayed. And you're basically doing that to explain your future self what you did in that part of the code. Okay, last. Yeah. Okay. So does watching award-winning fiction on television help us to understand other people? Psychologists Jessica Black and Jennifer Barnes tested whether people who watched award-winning fiction on television shows like Mad Men or The West Wing performed better on a test of theory of mind compared to people that watched documentaries like Shark Week and How the Universe Works. After randomly watching either a high-quality fictional show or documentary, participants were asked to look at a series of 36 photos of people's eyes and decide if each person was jealous, panicked, arrogant, or hateful. Scores ranged from 0, guessed the emotions correctly, or 36, guessed every emotion correctly. The data below approximate the actual means and standard errors. This is why I like the Norton and Heinzen book, because it has kind of, it has a couple of not so good examples, but sometimes it has a couple of really cool examples in a way. So these are actual studies that have been conducted, and they have gotten a hold of this data. So let's assume we are now to compare these respondents. So we have here 4, 8, 9 respondents that watched Mad Men and what else, West Wing. And then we have here 8 respondents that watched Shark Week and How the Universe Works. So do we think there's a difference? We don't know, right? But it's 2 different groups. It's independent people. Ergo, we're gonna use an independent sample t-test. So now if we build an average of these should be different. So we build an average of TV fiction and we build an average of documentaries. So and we see now that there's a small but marginal difference, small and marginal. Okay, so it seems like people who watch TV fiction have a better perception of people's emotions just by looking at their eyes. Whatever that means now, the interpretation I leave to you, but it's kind of funny to see an example like that. Good, okay, so we want to know now whether there are differences. And you remember the independent sample t-test, right? You remember that the calculation was a little bit more on the complicated end. It's not like that when you do it with Excel, because you can easily do this. Okay, again, t.test function. We have an array 1, which basically is all our 9 respondents to TV fiction. Array 2 is our second cohort that watched Shark Week, and these are these 8 guys. We do a 2-tailed test, as always, and we need to determine another type. So again, types, we have 3 possibilities how to determine the type. One is paired, which we know we wouldn't use here because it's 2 independent cohorts. We can do two-tailed equal variance or 2-tailed unequal variance. So why are we already a priori knowing that it will not be equal variance? Because it's different sample sizes.
It's 3. We're typing in 3.
We're typing in 3, yes. So it's unequal variance, also called the Wilks test. Okay. So there are for dealing with this, we have calculated these aliquots. You remember degrees of freedom of the respective sample divided by the total degrees of freedom, and then from the second sample again the proportion of the total degrees of freedom. So to deal with that, there are different arithmetic approaches. Excel is using here 1, so we get a p-value using the t-test function of 0.37, which essentially institutes or represents a significant difference. So we know now that these differences here of 1.5, which is that minus E13 minus A13 is minus 1.5. So we have a difference of 1.5 of score, whatever the score is. And that's significant different at an alpha level of 5%. So we do have a degree of our dfx is here 9 minus 1. So it's 8. Our dfy is 8 minus 1, which is 7. So it's 8 and 7. Our df total is 15. So we know for a degree of freedom of 15, if we go backwards, we have a degree of freedom of 15. At a p-value of 5%, our t-score needs to be at least 2.13. With the t-test function, unfortunately, I only get the p-value, but it would need to be larger than 2.14. Good. So now we go into R, and we do the same exercise here in R. So line 38. Line 38 and 39 builds our object, df3. It's 9 observations of 2 variables. If you look at this a little bit more, it's the same data. One thing that's different is that we have here something that is labeled NA. NA means not available, and is the way how R codes missing values. So since this is a different way of depiction as the tables that you have in an Excel spreadsheet, it always needs to be equal length if you put it in one data frame. Arithmetically, it doesn't make a difference. It will deal with it, and it will know how to deal with it. The only thing you need to do is you need to add NA.R. So whatever calculation you do, if you do a mean of DV fiction, you get a mean of DV fiction. So that's our DV fiction in the data frame 3.
Oh yeah, I didn't get that.
Hmm?
I got 48.
So if you do df3, just write df3 in the console, you get exactly that data frame we just looked at. Yeah, just df3, just df3. If you do df3 $ TV fiction, you only get TV fiction. Just write df3 $ TV fiction.
No, I did.
Just write it in the console.
I did control enter on 49 by accident.
That's fine.
Wait, what did Q?
Yeah, don't
Wait,
get
I didn't
confused.
follow the NA situation.
Yep, the NA situation is not available. So that's what we're getting to now. I would want to just quickly explain this. So you have basically, if you run df3,
What did you do before that?
nothing. I just ran 38 or 39. So if you 38 and 39, just select those 2 lines and press Control and Enter. You basically create a data set that you then call by just writing df3. If you write df3 in the console, it will display exactly that. And these are the 2 columns. These are the 2 quote unquote vectors that you're displaying now. If you only want to have one variable depicted, like only a TV fiction, you just write df3 $TV fiction. It will give you the TV fiction only. So you're addressing each of these sub-objects contained in that object individually. Yep.
So to get the columns, you did control enter on 48 and 49 together?
No, you do 38 and 39. You get this df3. This is here in the environment.
Yeah.
Yeah. If you want to then call the object and just like show me that object, you just write the name of the object. You can do this with df3. You can do this with df2. You can do this with df1. It will display it.
On the bottom, it's not in order.
Doesn't matter. On the console, you can just play around. Doesn't have ramifications. Well, does have ramifications, but not the way we use it. Okay, if you do df3 and you press $, this will pop up. So it gives you already a choice, and this is why RStudio is nicer than R, because it gives you that choice because the compiler stuff. So you can choose here TV fiction or documentary.
Oh, we already did that.
And if you select either of these and press enter, it will give you an overview. It will show that exact variable.
Wait, what about?
Just do df3 $. df3 $.
Just do that in the
Yep.
console? Yeah.
Did you run df 38 and
I
39?
ran 30 and 39.
Then you can do
So
df3 and you can,
what I did?
Yep.
The $.
yeah. With $, you get the sub object. Just select one of those.
Oh, TV fiction.
I accidentally ran 48.
Wait, then what do
Fine.
I do?
Don't worry.
You
Okay.
have to read TV fiction, then
Yep.
what do I do?
And
Enter?
well, so yeah, press enter.
Are we done now?
No. So if we do, if we do now mean of TV fiction, it gives you the average of TV fiction.
How do we do that? Like, you write that in?
Run line 48. So now one problem persists, which is with documentary. So if you do the same with documentary and you write mean df3 documentary.
Oh, we write this in?
Put
Wait,
this
where? In the console?
in the console, yeah.
So should we do the one that we didn't do yet?
Because-
If I did TV fiction.
No,
I should
just
not
do-
do-
You just do documentary, just write that. Mean df3 documentary.
Okay.
Because this is where you run into a hiccup. You get an NA as a result.
Yeah.
And the NA is caused because there's missing value in there. And this is what this addition here means. The NA.rm equals true. This means remove NAs. If you run line 49 with the NA.rm equals true, which is the same as the one we had before that resulted in
But
NA.
then I got it.
Now we're getting it because it removed the NAs. It removed that missing value. That's what you did.
What was the last line we're supposed to have?
Just did 49.
So
49.
if you run now 48 to 51, you basically get all two means and you get the standard deviations through. So now you run line 53 and 54.
And now we're done.
After the NA part, just go, just run 48 to 51.
Okay, you do.
And if you next go on the two sample t-test, this will give you exactly those results we had before in Excel.
And then how do we? I didn't get that. And then you round the
53 and 54.
And then what?
These two will give you exactly. So you get a p-value, you get a t-score, you get a degree of freedom. And here it's getting tricky because the degree of freedom is not consistent with what we found. We found a degree of freedom of 14. R finds a different one because R is using mathematical function to estimate the degrees of freedom because what we are doing is just an approximation. R is doing it more detailed and more accurate, but that's a whole different conversation. Good. We get a confidence interval which does not include the zero, so we know there's a significant difference, not taking zero. Under the null hypothesis, it would be they're equal to each other, but we know they're not, and we see the differences. Yes.
provided for you run it in text edit or script edit?
Text edit.
But how do you do that?
Yeah. So now we get back to the deliverable. We have 9 more minutes to do that. Hmm? Oh, does it? Oh. Okay, so we do Control L on the console. We click on the console, we press Control and L. We're clicking now on the script.
We just click randomly on the console anyway.
Yep. Control and L.
And
Now we click on the script on top, left upper quadrant.
Yeah.
We press Command and A, or Control and A for the Windows users. We press Control and Enter, and we get our printer. So this is the entire code. And now we're copying this into a text edit, which we find from the Spotlight.
Mine's not an error.
Not good.
It's okay.
No, that's not good.
Not good.
Not good. There should be no error. So we open the text. No, we need Command A or Control A. We're running this with Control and Enter. Then we're copying everything from the console into a text file. Okay, once again. Okay, everybody pay attention now. This is practice lab 3. This is 10 questions, and you have the recording. Okay, we're clicking on the console, Control and L. We're clicking on the script, we're pressing Command and A, or Control and A, we're selecting everything in the editor. We're pressing Control and Enter, we're running this. And then we're copying everything that's in the console with Command and C like Caesar. We open the text edit, and we're copying this in the text edit file. For Mac users, it will look like that. You click on New Document, and here you just press Command and V. Correct. We're putting in the title of the file. We're writing it in exactly the same fashion as the last one. We're writing STAT1021. We write the family name, and then we write Practice Labs 3. Good. Yes.
I started
Wait, let me just stop the recording. All right.
after